Last week we talked about category or quantitative variables, excuse me. So, and like kind of how to display them. But here this week we're going to talk about relationships between categorical variables. So those are going to be our variables that involve groups or labels, didn't really have any value to them per se. So that is what this week's lesson will be on. So these are just different ways I'm showing you here that we can show or like display categorical variables. So this is if you had a variable that you knew was categorical, so it was a group or something that was just, so for example, like flavors, colors, something like that. Those are going to be our categorical variables here. And if you have those, you're able to put them either in a contingency table or set a cluster bar graph. So our bar graph is the same situation as a normal bar graph, but in this case, the only difference is that we have two categorical variables. So in this case, they're looking at education level and then gender. Those are the two different categorical variables we have. And then in the contingency table, we have cases and controls as our one variable, like whether or not it's a case or control. And then if it's exposed or not is our other categorical variables. And those are definitely categorical because exposed or unexposed, kind of yes or no. Same with case or controls, you know, is it controlled or not? And that's just kind of representing too where you see the totals like A plus B, whatever that is. So that's just showing you basically how you would get the value in that specific box there. So those are just ways you can display categorical variables. Okay, so risk and odds, these are both very similar. So it's important you kind of understand the difference between them. Where it comes from, where how they're both describing the likelihood of an event, but we want to make sure that we're talking about and looking at the bottom, the denominator here, so of these equations. So here we have, like I said, these are both describing the likelihood of an event, but for risk, our denominator here is going to be the total number of outcomes. So that's why it's just talking about the probability that an event will occur just in general, because it's the number with the outcome, so the amount, the likelihood that it occurs, and then divided by the total number, so it's just occurring in general because we're using the entire amount of outcomes. So the difference then for odds is if we're trying to compare the odds of it happening versus not happening. So we're trying to see if there's a difference there, the difference between it happening or not happening. And the way that we change that there is by going and making our denominator, instead of the total number of outcomes, our denominator here is going to be the number without the outcome. And so that's how we're able to make that comparison between the likelihood of an event happening versus not happening. So yeah, that's the main idea there. And then another way you can write the odds is by doing risk divided by 1 minus risk. And because if you think about it, risk is our probability that an event will occur. So technically 1 minus the risk would be all of basically the number without the outcome, everything like that didn't occur. So that's why you're able to put that, also use this equation at the bottom here to describe that. Okay. Here we go. Okay, so, oops, I just clicked something. Hopefully it wasn't bad. Okay. All right. So if we're talking about risk between groups, so remember our risk is just the probability that an event's going to happen in general. And then we have two different types of risk. So relative risk is basically when we're comparing these two different risks. So the risk of one group and then divide by the risk of another group. So we're trying to, and the interpretation is that group one is this many times more likely to experience the event than group two is. So let's say you're looking at males and females and maybe the rate of heart disease or something. When you're trying to find relative risk, you're trying to find the risk of this event. So for example, heart disease in terms of the different groups that you have, or, so you're trying to find the risk of the event in terms of the different groups relative to the different groups you have. So the risk of heart disease relative to gender. So that's how you'd be saying, females are this time more likely to experience heart disease than group 2. So that's the main part there, is that we are comparing one of our categorical variables there. We're taking the risk of an event happening and then comparing it between the two parts of that categorical variable. It doesn't have to be gender, but that's just an example. And then increased risk is basically exactly what it sounds like. So remember, relative risk is, if we're comparing the two groups there, and we want to, and then if, in this case, if we're trying to see, if we're comparing them, but we also want to see, how much more likely is it to happen, then we're able to do increased risk. So you just take whatever your relative risk is minus 1, and that's going to be able to tell you the increased risk. So how much times more higher is it to happen to group 1 than group 2. So that's the main idea there, is just we're trying to talk about how much has the risk increased in comparison to the group. So relative risk is just comparing the groups in general, like their risks in general, but increased risk is going a little more in depth and saying, well, how much more is it likely to do this? So that's more on risk. Okay, so Simpsons Paradox is something, it's just a statistical concept that's discussing that that there could be, observed association between these two variables, but it could basically change, or it can even reverse in some situations when there's like a third variable interacting. So this is similar, if you remember confounding variables, it is similar to that. Because we're looking to see if, we have this association between these two variables, but maybe there is a third variable that's influencing it. So confounding variables, that was, it's a similar concept, that there's that variable that was influencing your other variables that you weren't testing or looking at. So I've used the example before where, let's say you had your two variables are race and then your opinion on the death penalty. And let's say you're trying to compare, see, if there's an association between someone's race and then their opinion on the death penalty. Simpsons Paradox says that there could be another variable there that is basically influencing this decision, and it's not necessarily showing you an association between race and opinion on the death penalty. It might be also showing you the interaction of another variable. So, for example, a third variable, such as the victim's race, could be something that's influencing that. So maybe, there's not a correlation between, the victim's race and their opinion, because maybe the correlation is shown between the race and then like the victim's race. So if someone's white and the victim was also white, maybe that'll change their opinion on the death penalty than if they were white and Hispanic or something, or any two different races together. So it's just saying that there could be a third variable that is influencing the two that you're trying to look at. So in reality, it can basically, and in this case, it could really reverse the direction, because it could make it look like, because if race and opinion on death penalty, maybe that's a negative correlation, like they're not really correlated, people in general, like if we were to actually find it that way. But victim's race, maybe that is highly correlated, so it could be showing you a complete opposite direction, like maybe those are really connected. So you're kind of getting an unrepresentative correlation there. So that's the main idea there. Okay. All right, so we'll do some review questions now. So we'll go ahead and I'll read these over and then let me know what you think about them. So our first one, we have, according to a pilot study, among those who use anabolic steroids, a chance of future heart disease increases by about 15%. So in this study, what type of statistic is 15%? So let me know what answer you think it is for this multiple choice question. Okay, good. So you definitely have a concept that this is risk in the fact that we're talking about the probability of it happening in general. But we want to make sure that we are looking at every part of this where it also says that the chance of it increases by 15%. So in this case, we just want to make sure that we're identifying that this is also talking about increased risk because we're talking about how much it's increasing. It is talking about the chance of something happening, which is risk. But then since it says increases, we're seeing how much it actually increases, how much the chance increases. That's why it'd be A, increased risk. And it's just presented as a percentage increase here. Does that make sense? Awesome. Okay. All right. Let's do another one. Oops. Okay, so which of the following statements is true? So we can have a relative risk value larger than 1, we cannot have an increased risk value at 0, or we can have a negative odds ratio. So which one of these is true? All right, great job. Yep, so our answer is A here. So if we look at this, remember when we have a relative risk, that's going to be our ratio of the risk. So it can be larger than 1 because remember, if our numerator is higher than our denominator, we can have a relative risk that's larger than 1. So if our risk of it happening is larger than, or the amount that happens is larger than that denominator, then in that case we are able to have a larger number than that. So the risk of group 1 is larger than the risk of group 2. That is possible in that case. So A is the answer. This is true. The rest of these are false. We can have an increased risk value of 0. That just means it didn't increase. And then we can't have a negative odds ratio. That does not make sense. So, all right, good job. Okay. All right, a reported study has found that males are 2 times more likely to have high blood pressure than females. What quantity is being reported here? So let me know what you think about this one. All right, great job. Yeah, so if we look at this, so remember this is saying that males are 2 times more likely to have high blood pressure than females. So remember, relative risk is our ratio of the risk. So we're saying that group 1 is this many times more likely than group 2 to have whatever the other variable is. So in this case, we have males and females. That's our the 2 different groups, and then we do have more likely to have high blood pressure than females. That's going to be our, or high blood pressure is going to be our other variable that we're looking at. So this is talking about relative risk. It's not increased because it's not talking about how much it increases at all. And then it's also making sure we're not talking about a comparison, because risk isn't a comparison between groups like the statement doesn't have that relationship there. It's just talking about like the probability of something happening in general. But here, since we have that comparison, we do have relative risk, which is going to be B. So good job. All right. I think we have another one. Okay, so suppose that 45% of people frequently exceed the speed limit. A random sample of 100 people is surveyed, and 60% indicate that they frequently speed. So what is the value of the population percent given to you in the problem? So try this one out. Okay, so I definitely see why you said that. So if we look here, remember our population is going, or like whatever the percent that we're given, that's the population percent, is going to be our overall population. It's taken from the overall population, so it'll be the percent of the population. So if we look in this first sentence here, we have 45% of people frequently exceed the speed limit. So this is our population because it's just saying of people in general. And then the 60% came from our sample. So we know it's not 60%, so it definitely can't be C or A because that's about our sample and we're asking about the population. So in this case, all they're asking for is the population percent. So we don't really need this plus or minus 0.1 down here because all we're asking for is for the percent. So the percent in general is just 45%. The 0.1, I mean, that would come if we were talking about different, the standard error or something of with the sample size. But since we're not looking at the sample size, or since we're just looking at the population, that sample of 100 people doesn't really apply in this case, so we wouldn't really need this down here. So that's why it wouldn't be D. So our answer would be B. That's going to be our population percent, which is 45%. Does that make sense how we got that answer? Hopefully. Okay. Yeah, of course. Yeah. Okay. Yeah, I see where you got that from. So, but yeah, you always want to make sure, since it says a random sample of 100 people. So that means they took 100 people from the population. So you always want to assume you're not necessarily gonna have a as if it says a number after like a random sample, that's going to be your sample's size from your population. Often if you see something that doesn't have a number with it, if it just says all Americans or everybody who attends Penn State or something like that, if you see a general statement like that, you're probably going to be talking about a population, because they're not giving you like a specific number, because they're just talking about everybody. But since they gave you, I mean, you could have a specific number. The total amount of people at Penn State is 46,000, and a sample of 20,000 was taken. We still have that population as being that 46,000 all Penn State people, but then our sample would come from that. So yeah, look for more general statements that kind of cover everyone, and that's going to point you towards what your population is, and then you won't really ever have to worry about sample size or anything, because that won't apply in that case. So All right, good thinking. Great job. All right, I think we have two more. So let's try this one. So a study done by the Ohio State University Medical Center examined whether or not taking aspirin a day would help colon cancer patients reduce the chance of getting a subsequent colon polyps. 635 patients with colon cancer participated. 317 of them were randomly assigned to the aspirin group, and the other 318 patients were assigned to a placebo, and so the non-aspirin group. The placebo, remember, is where they don't receive the treatment. So 54 patients in the aspirin group developed subsequent polyps compared to 86 patients in the non-aspirin group. Many confounding variables were controlled for this well-designed randomized experiment, so you don't really have to worry about that there. So basically look at these and see, we're trying to figure out the percentage of all patients basically that didn't develop the polyp. So try to decide, let me make sure this is like clear here. So we're trying to find percent of all patients who didn't develop polyps. So who didn't. Okay. So we're looking for this number here. So go ahead and look at your options here and see which one of these you think is representing the percent of all patients who didn't develop it. So let me know what you think about this one. Okay, so I definitely see your thought process there with C. So remember, so we're looking for the percent of all patients who didn't develop the polyps. So first what we want to do is figure out how many is all patients, like how many patients would that be? So in this case, we have 635. That's going to be all of our patients because it says that's how many people participated. So we know that's going to be our denominator because we're always dividing by the total number. So that's going to be 635. And then our numerator is going to be the percent. So we're trying to look for the percentage of those who did not develop the subsequent polyps. So we want to find the total number that did not develop it. So if we look at this table here, the total number who did not develop it is going to be our 495. So this is going to show us the amount that we're looking for, so the amount that didn't develop it divided by the total amount, which is going to give us the percent that that didn't develop it. So here's like our total, and then this is going to be our numerator because it's the amount that we're basically looking at. So the answer is actually D because none of these are correct. We want to make sure our denominator is always talking about the total number of patients. So in this case, really only our option would have been A at first, because that's the only one with the denominator having that, but the 140 is actually going to be the percent that developed the polyp, so that's why it wouldn't be A, because we're looking at the percent who didn't develop the polyp. So that's why D is the correct answer, because this would be the correct proportion that we would use. So this would be 77.9%. Does that make sense how we did that? Hopefully. What will choice C? Choice C. Yes, good. So yeah, that would be relative risk, because we're talking about those who developed versus those who did not develop it. So yeah, it's comparing the two different groups there. So yeah, good thought. So yeah, and also technically you could, if you're looking for, you know, if you're trying to look for, I guess, odds of the odds that you develop the polyps, that would be, you know, the 140 divided by the 495, because the 495 is the amount without the outcome. The 140 is the amount with the outcome. So that's why you divide those two. But good thinking. All right, cool. All right, I think I have one more. So study found that many smoked are 1.5 times more likely to have lung cancer than those who did not smoke. So the number 1.5 is which of the following? So go ahead and let me know what you think about this one. Yay! All right, great job. Yeah, so our answer is A here, because once again we are comparing gender, and then, well, and I mean, so we have men who smoked and then those who did not smoke. So we're comparing smokers and not smokers, and then whether or not they get lung cancer. So since we're comparing those two groups, we do have A, and this is not talking about, we're not talking about increased risk at all. We're just talking about comparing the two groups and the risk from one to another. We don't see the word increased in there, so it's not B. And then it's not talking about, and also, I mean, it doesn't indicate a percentage. So, and then also baseline risk, that's basically if we were, you know, doing a comparison between the groups and just in general without, you know, comparing them with this 1.5 times more likely. So remember, this is what, that's like common language that we use for relative risk there. So A would be our answer. So great job. All right. So, okay, so obviously go ahead and check this out, and all the other videos for the other chapters in the midterm one. Review 2 is on there on the YouTube channel, and that link is also on the stat page for your notes. And our next group review for chapter 8 will be next Thursday at 8:30. So if you haven't already, I think, yeah, you gave me your Penn State email, which is great. If you have any other questions at this point, let me know. If not, you are good to go for tonight.